Very good morning, dear students. In this video, I am going to continue with the topic, that is D and F block elements. In last session, we have seen about a few important topics related to this D and F block elements. Now, still I am going to continue with the same topics. See, firstly, from this chapter, you are going to get totally 8 marks. So, if you divide this chapter into two parts, from D block elements you will get 6 marks, from F block elements you will get 2 marks. Okay, so usually you will get questions from this chapter in two parts, that is part B and part C. So part B question is from F block element, that is question number 14 for 2 marks. And part C questions, 2 questions will get from D block elements, that is 23 and 24 for 3 and 3 marks. Okay, so totally 8 marks will be from this D and F block elements. So now we'll study about the properties. Now see, if you see the properties of 3D series elements, okay, 3D series elements we know that are from scandium to zinc with the atomic number 21 to 30. Okay, whatever the elements exist or present between 21 to 30, that is scandium to zinc, they belongs to 3D series. Okay, now we want to discuss about these 3D series elements are also known as first series elements. Okay, first we will discuss about their atomic size, that is atomic and ionic radius. If you observe, usually along the periods, okay, along the period, always the atomic size increases with increase in the atomic size decreases with increase in the atomic number. Usually atomic size increases with increase in the atomic number. I am very sorry, listen carefully. Along the period, always atomic size increases with increase in the atomic number, because once the number of electrons increases, the entering of electrons in different subshells also increases, automatically their size also increases. But in the case of D block elements, this case is completely different. Okay, this case is completely different. Along the period, this atomic and ionic radii decreases. Okay, decreases with increase in the atomic number, because the electrons enters into the same subshell, that is 3D series or 3D orbital. The electron enters into the same subshell, that is 3D series or 3D subshell, so that there is no much increase in the atomic size. Instead of that, there will be some decrease in the atomic size. And remember, but this variation is not at all regular. It is not at all regular. Okay, usually atomic size should increase with increase in atomic number. Okay, but this condition is completely not applicable in the case of 3D series elements. Okay, in this 3D series elements, the number of electrons gradually adding into the same subshell, so that there will be some decrease in the atomic size with increase in atomic number, but this variation is not regular, it is irregular. Now we will see in different types of elements in 3D series. So these are the elements present in 3D series: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay, so atomic number of scandium is 21, atomic number of zinc is 30. So for these 3D series elements, now we want to observe the change in atomic size. See, for the first elements, okay, for the first elements, always the atomic size decreases. The atomic size decreases because, okay, that is from scandium to manganese, because due to having more effective nuclear charge, okay, due to having more effective nuclear charge, once the nuclear charge, effective nuclear charge increases, atomic size decreases. Once the effective nuclear charge increases, atomic size decreases. For the first 5 elements, okay, for the first 5 elements, this effective nuclear charge is more, thereby the atomic size is less. Okay, now see the first for the next few elements. Next few elements are nothing but iron, cobalt and nickel. Okay, for these elements the increase in the size or decrease in the size becomes almost constant. This is due to becoming equal of this effective nuclear charge with the shielding effect. Okay, this is due to equaling of effective nuclear charge with the shielding effect. Okay, about shielding effect we'll see later. Understand? See, number of electrons increases, shielding effect also increases. See, till 5 electrons, only 5 electrons will be present. Once the number of electrons increases in the d orbital like 6, 7, 8, 9, 10, shielding effect also increases. If you observe the shielding effect in case of d orbital, so different types of orbital, s orbital is having more shielding effect than p orbital, than the d orbital, than the f orbital. That means d orbitals are containing less shielding effect than the s orbital. Okay, for these three elements, effective nuclear charge becomes equals to this shielding effect. Okay, almost equal. When these two become equals, there is no increase in the atomic size or decrease in the atomic size, even that becomes equal. Okay, now move on to the next two elements, that is copper and zinc. In this copper and zinc, atomic size increases. Okay, this is due to interelectronic repulsions. Okay, see, after copper and zinc, so pairing of electrons will start. Once the pairing of electrons, number of electrons are getting paired, the interelectronic repulsions also increases. Once interelectron repulsions increases, shielding effect also increases. Okay, once the shielding effect increases, atomic size also increases. Remember, shielding effect and atomic size is directly proportional. Effective nuclear charge and atomic size is inversely proportional. Understand? For scandium, from scandium to zinc, atomic size is not, there is no regular change in the atomic size from scandium to zinc. For first few element, atomic size decreases due to increase in the effective nuclear charge. For the next three elements, it becomes almost the same, because in these three elements, effective nuclear charge becomes equal to shielding effect. Whereas for the last two elements, interelectronic repulsions are more due to increase in the shielding effect. Okay, so that is about the atomic size of d block elements. Okay, that to 3D series elements. Possible, okay, it is possible only up to 3D5. If electrons get paired, okay, if electrons get paired, automatically shielding effect increases. There is rise in the atomic size also. See, once again I am repeating about this atomic size. See, it always depends on the effective nuclear charge and shielding effect. Once effective nuclear charge, this is inversely proportional to atomic size. Once effective nuclear charge increases, atomic size decreases. If it is less, it is more. Whereas shielding effect is directly proportional to atomic size. You just remember these two. Okay, when this shielding effect increases, whenever number of d electrons increases, shielding effect increases, atomic size also increases. In the starting elements, effective nuclear charge is more predominant over the shielding effect. So that due to increase in the effective nuclear charge, atomic size gets decreases. Whereas for the middle elements, these two are equal. Then there is no increase or decrease in the atomic size. Okay. Now we'll move on to the next property. Now see the next property, that is ionization enthalpy. What is meant by ionization enthalpy? The general definition is that the amount of energy which is required to remove the outermost electron from its gaseous state is known as ionization enthalpy. It is the amount of energy required to remove the last electron from the outermost orbital is known as ionization enthalpy. Okay, along the period, this ionization enthalpy increases. Remember, only for the D block elements I am telling. So along the period, ionization enthalpy increases. This is due to decrease in the atomic size. Whenever size decreases, the attraction between the last electron and the nucleus increases. Okay, we have to overcome this attractive forces to remove the last electron. If size is very less, attractive forces are more, then it requires more amount of energy to remove the electron. Thereby, ionization enthalpies increases due to decrease in the atomic size. Okay, and in another reason for increase in the ionization enthalpy is due to increase in effective nuclear charge. Okay, now even this ionization enthalpy change is not regular. It is not regular. It increases up to chromium due to increase in the effective nuclear charge. It increases up to chromium due to increase in the effective nuclear charge. And there is gradual increase after chromium. This is again due to shielding effect of 3D electrons. Because of having shielding effect of 3D electrons, even for shielding effect of 3D electrons, this ionization enthalpy gradually increases even after chromium. Okay, now we'll move on to the next property, that is metallic nature. If you observe metallic nature, all are metals. Okay, all these metals are known as transition metals. So this metallic property of D block elements is mainly due to decrease in the ionization enthalpy. This is less ionization enthalpy when compared to S block, P block and F block. Don't confuse here and here. Here we are just comparing along the period within the same D block elements. But here we are comparing the ionization enthalpies of D block elements with other block elements. If you compare that, these D block elements are containing less ionization enthalpies. Due to low ionization enthalpies of D block elements and presence of unpaired electrons. Okay, so due to having unpaired electrons, they are ready to make a metallic bond and they can show metallic character. So for showing metallic character, there are two reasons, that is due to having less ionization enthalpy and presence of unpaired electrons. And these metals are hard metals. Okay, these metals are very hard. This is due to the formation of strong metallic bond. Okay, this is due to the formation of strong metallic bond. They are acting as hard metals. Okay, so that strong metallic bond is due to the presence of again unpaired electron. Now melting point. If you observe melting point, it increases up to chromium. Melting point increases up to chromium. This is due to containing unpaired electrons. Once number of unpaired electrons increases, automatically strength of metallic bond also increases. See, listen carefully. Melting points are increased up to chromium, scandium to chromium, because from scandium to chromium we can see D1 to D5 electrons, which are all unpaired electrons. Okay, once number of unpaired electrons increases, strength of metallic bond also increases. After chromium, this melting point gets decreases and it is minimum and least for manganese. Okay, because manganese is existing in stable configuration, that is 3d5 4s2. Due to exist in stable configuration, that is 3d5 and 4s2, it can show very less melting point because containing less tendency to form metallic bond. To make metallic bond, what it requires? Unpaired electrons. But all these unpaired electrons are not ready to participate in this bond, because to maintain the stability, they should be existing in the same configuration. So that manganese is the element which contains least melting point. Next, move on to the another one, that is from manganese to the next elements. Okay, from manganese to the next element, again this melting point changes, increases. Starting decreased, then maintain minimum, and again it decreased. Okay, at the end, that is, what is the end element? Zinc. That last element contains least melting point. Remember, only manganese to nickel it increases. Again for the zinc it is least. This is due to the number of unpaired electrons decreased. Okay, in zinc, what is zinc electronic configuration? 3d10 4s2. In this case, all the d electrons and s electrons are completely filled. Number of unpaired electrons, what happened? Decreased. Once the number of electrons decreases, strength of making metallic bond also decreases. Automatically, to break this weak bond, it requires minimum amount of energy. Melting points also decreases. And if you plot a graph for this, first from scandium to chromium, it's gradually increases. Chromium is containing the highest melting point. Okay. Why it is containing highest melting point? Due to containing maximum number of unpaired electron. Again, from chromium to manganese, it decreases. Why this is showing least melting point? Because of containing this stable configuration. Okay, and from manganese to again it increases. If you come for zinc it becomes minimum. Why it is becoming minimum? Due to containing stable configuration, that is 3d10 4s2. There is no unpaired electron here to make a strong metallic bond, thereby automatically its melting point decreases. Okay, this is about the melting points. Now we'll move on to the next property, that is oxidation state. Actually, about this oxidation state I already explained in the previous video. Now we'll just make a glance look for about this oxidation states. So these d block elements can show variable oxidation states. Okay, variable means different oxidation states. The reason behind showing this variable oxidation state, it's due to less energy difference between the valence shell and penultimate shell. Okay, so less energy difference. What is valence shell? Ns is the valence shell, N minus D is the penultimate shell. If you see the energy difference between these two, that is very less. Due to having very less energy difference between the valence shell electrons and penultimate shell electrons, almost all of the electrons tries to participate in different bond formation and can able to show variable oxidation states. Okay, if you consider specifically 3D series, okay, 3D series, its configuration is 3D 1 to 10 and 4s 1 to 2. So this is valence shell and this is the penultimate shell. Between these two, energy difference is very less. Due to having very less energy difference between 3D and 4s electrons, all the 4s and 3D electrons tries to participate in bond formation and can show variable oxidation states. And if you see middle elements, okay, maximum variable oxidation states can be shown by the middle elements. Example, see these three, scandium, titanium, vanadium, zinc, copper and nickel are said to be extreme elements. Okay, they are extreme elements. These extreme elements always show less oxidation states. Whereas middle elements like chromium, manganese, iron and cobalt, they can show maximum variable oxidation state. For example, if you consider manganese, this manganese is the most important 3D element which can show maximum number of oxidation state as well as it can show highest oxidation state. So maximum number in the sense it can show all the oxidation states of 3D series, that is ranging from +1 to +2. Sorry, +7, that is +1, +2, +3, +4, +5, +6 and +7. All these oxidation states can be shown by the manganese. Okay, now next another middle element is chromium. Even chromium can show maximum oxidation state, that is from +2 to +6. Next element is iron. Even iron can show +2, +3 and +6 oxidation states. Okay, so this is about the oxidation states. Here two important questions are there. First one, what is the reason to show variable oxidation states? This is only the reason, that is due to having very less energy difference between the penultimate shell and valence shell. If the question is asked for 3D series, why 3D series elements can show variable oxidation state? Reason is that due to containing very less energy difference between the 4s and 3d orbital or subshells. Okay. Another question is that which element can show the highest oxidation state and maximum oxidation states? That is manganese. Okay, these two are very important questions, you just remember. Okay, now we'll move on to the same compounds formed by the oxidation states. Whatever the compounds with low oxidation states formed by 3D series elements, they are ionic in nature. Compounds with low oxidation state. Compounds with low oxidation states are ionic in nature. Compounds with high oxidation states are covalent in nature. Compounds with high oxidation states are ionic. Remember, for example, +6 and +7 oxidation state compounds are covalent in nature. Lower positive oxidation states formed by the compounds are ionic in nature. There is one exception for this 3D series oxidation state, that is iron, for iron and nickel. These two are the elements which can also show another extra oxidation state, that is zero oxidation state. Okay, zero oxidation state can be shown by iron and nickel. For example, in carbonyl compounds, FeCO 4 times, NiCO 4 times. Here carbon monoxide or carbonyl group is a neutral compound, then the oxidation state of nickel and iron is said to be 0. That means this iron nickel are having the property even can show zero oxidation state along with the other oxidation states. Okay, so that is about the few important general properties of 3D series. Okay, we'll meet in another video. Thank you.